It's on, yeah. So Larry has heard an earlier version of this talk, and I think that's how he knew to position me right after Mark Fishman and right after lunch, because Mark's talk is a perfect prelude to what I'm going to talk about, much earlier stage of the same kind of clinical story. And lunch, which you all just had, is very closely linked to the subject of this talk, because on average, you had a gram or two of linoleic acid, maybe more if you had things like potato chips. And linoleic acid is an essential nutrient. You have to eat it every day, pretty much, as I'll explain why. And that's unfortunate, as you'll see, because it leads to a lot of problems. Okay, so by way of introduction, first of all, I've always, through my whole scientific career, if something sounds too good to be true, it is too good to be true, okay? This is going to sound too good to be true, okay? But I'm hoping, and I'm convinced thus far, it's actually real, okay? Now, in 2013, some of you were here, many of you were here, I gave a lecture on non-invasive prenatal diagnostics. And it's only 6 years later, and I'm giving a lecture on neurodegenerative disease and drug therapies. And so you must be curious, if you've thought about this connection, how did I get here from there, okay? And there are two parts to the story. The first is that this is not my scientific idea. I'm the entrepreneur as much as the scientist for this project. The idea came from a chemist named Misha Stepanov, who worked for me at SEQUENOM. It was one of the people developing some core chemistry which SEQUENOM used, and left, went off and did various things, and one day wrote me an email with the idea that generated everything I'm going to tell you today. It's really a spectacular, and as you'll see, unbelievably simple idea. There's a second connection, which you'll see momentarily. Okay, so take a deep breath. It's bad for you. You probably just shortened your lifetime, maybe by a few minutes. How could this possibly be, okay? How could it be that breathing is bad for you, and also that the linoleic acid you had for lunch, which, by the way, mostly comes from corn oil in the Western diet, how can that be bad for you? How did this happen? Well, we're going to talk about lipids, fats, okay? It's a very unpopular topic. Most people fall asleep during biochemistry courses during this part of the curriculum, okay? But fats are extremely important in two things that we care about very much, our brains and our eyes, okay? And a lot of the solid weight of brain and eye are made of fats, lipids is the formal term. And the two that you need to know about are linoleic acid, which I've already told you, and that's, by the way, called an omega-6, those of you who may take supplements. And then DHA, which I won't even tell you what it stands for, but that's the major omega-3, okay? That a lot of you probably take as supplements, and you may stop taking as supplements by the time I finish this talk, okay? Okay. Now, everybody knows that fats go rancid, okay? The reason why fats go rancid, the fats that do, not all of them do, but most of them do, is because they oxidize. They burn. And different fats are flammable to different extents. And the linoleic acid, I guess I have a pointer here, right? Yeah. Oh, wait a minute. No? Well, oh, sorry, yeah, right. The linoleic acid in green, that's what you had for lunch, is not very flammable. Well, you must be thinking, that sounds great. Unfortunately, what happens is you metabolize the linoleic acid into something called arachidonic acid. Your liver does this in most people over a period of several days. And arachidonic acid is terribly flammable. And the DHA, which some of you take as supplements or took as supplements, is the most flammable fat at all. So I guarantee if you're taking DHA supplements and you're not keeping it in the freezer, preferably under nitrogen, a lot of it is gone and is actually harmful, okay? Okay, all right, so how did we get into this situation where things we have to do, breathe and eat fats, are harmful? Well, to me, the most answers to biological questions, and I guess for Larry as well, come from evolution. And it seems that humans backed themselves into a corner in evolution, in relatively early evolution, by discovering seafood. And when people began to eat seafood, or I guess our simian ancestors began to eat seafood, it allowed the brain to develop more complexity, more complex connections, and it allowed the retina to develop and give us high-resolution vision, okay? And the fact that these fats are very prone to burn, and the burnt products are very toxic, extremely toxic, didn't matter, because everybody died before those toxic effects could set in, okay? If you see, if our lifespan were very short, as you'll see, we have no problems. And in fact, our lifespan was very short until roughly 100 years ago. Nobody lived long enough, on average, to get Alzheimer's or Parkinson's or all these other horrible things because they died in their 30s. What happened, you all know, of course, was that we began to discover sanitary procedures and antibiotics and eliminated infectious disease. And that led to a huge bump in lifespan. And projections are that it will go to 85. And something like a quarter of us will have Alzheimer's at that point. Okay, so that's the problem. The place where it occurs is in a little organelle called the mitochondrion. What happens in the mitochondrion sounds simple, but it's chemically really obnoxious, okay? So in the mitochondrion, what we do is convert oxygen, which you breathe, into water, which is perfectly safe. And if we knew how to do that in a single step, there would be no problem. But we don't know how to do it in a single step. It takes 4 steps, because for any of the chemists in the audience, it's a 4-electron reduction, okay? And although the oxygen is safe on the left and the water is obviously safe on the right, everything in the middle is devastatingly dangerous. Superoxide radical, hydrogen peroxide, kills things, and hydroxyl radical is actually the worst of all, okay? So these reactive oxygen species leak out to some extent, but more important, they damage the mitochondrial membrane, okay? And you'll see a little bit how that happens. And if there's any imbalance in this process, it leads to trouble. Either too much oxidation, not enough repair of damaged lipids, and you'll see eventually diseases that have both of these things. But the example I want to give you, because it connects with the talk I gave 6 years ago, is Down syndrome, okay? So in Down syndrome, you have too much superoxide dismutase because you have 3 copies of chromosome 21, and the gene for Down syndrome is on chromosome 21. But you only have 2 copies of catalase, which is on chromosome 11. So that flow I showed you on the previous slide is uneven, and you accumulate intermediates. Now, I'm not saying this is the only thing that goes wrong in Down syndrome, but it's probably why Down syndrome individuals almost inevitably develop Alzheimer's disease, because Alzheimer's disease is one disease that's highly linked to oxidized fats. So my dream, if all of this works out, is having developed methods with Dennis Lowe, who's in the audience and will speak tomorrow, having developed methods, and Chunming Ding also, having developed methods to diagnose Down syndrome very early, maybe we can start treating pregnant women who want to keep their Down syndrome fetuses with the drug I'm about to show you, and drugs that will be developed later, and restore a much more normal phenotype to that individual. I have no idea, but it would be great to try it. Okay, so if you read the literature of almost every neurodegenerative disease and many retinal diseases, it's full of references to oxidative damage. And I'm not going to bore you with references or reading slides, but if you do post-mortem analysis of Alzheimer's brains, what everybody is focused on in these protein tangles, but what stabilizes these protein tangles are crosslinks made by oxidized fats. Okay? So we don't know for sure exactly what's cause and what's effect, but the bottom line is these neurodegenerative diseases involve a lot of fat oxidation. Now, our brain knows this and tries to protect itself. Oops. Because 20% of the total energy used by the body is used in the brain. And of the energy that's used in the brain, a quarter of it is devoted to repairing oxidized fats, okay? So this DHA and arachidonic acid, which make up most of the mitochondrial membranes of your brain, are burning up all the time. And if you're young or if you're healthy, you spend all this energy to fix the problem, okay? This is the mess we got into, okay? But if anything is compromised, you're in trouble, okay? So linoleic acid, that's what you had for lunch. On the left, just so you see the chemistry. Don't worry about the one on the right. We're not going to talk about it. It's in your mitochondrial membranes. And what happens, here I'm sparing you the chemistry, but I'm just showing it to you schematically. When you oxidize a fat molecule in a membrane, it turns around and oxidizes the one next to it, and the one next to it, and the one next to it, hundreds to thousands of times. Okay? So it sets up a chain reaction, not unlike a nuclear chain reaction, in which a single damage event is amplified by orders of magnitude. Okay? Now, we know this. Your body knows this. You have something called vitamin E in your membranes, whose job it is to try to quench this. But the maximum amount of vitamin E that we know we have in membranes that doesn't start to distort their structure is 1 in 1,000. And so there's no way that that vitamin E can be where the first fat gets oxidized. So it's a relatively inefficient repair process, and again, it can be compromised. So this has been known for decades. Okay? Why haven't we been able to do anything about it? Well, all the drug companies looked at this decades ago and said, antioxidants. You know, let's make antioxidants. Let's try to make membrane-soluble antioxidants, okay? And it just doesn't work because you can't get the concentrations of these things high enough to quench this furious reaction without leading to disruption of the membrane, okay? And this has been known forever, and everybody's given up and gone on to other things. And here's where Misha Stepanov came in. And being a very good chemist, he realized that instead of trying to quench the oxygen species, why don't we protect the fats? Okay? So here's linoleic acid again. And the place where oxygen likes to work is on those two hydrogens. And he said, well, let's put deuterium there instead of hydrogen. And the deuterium carbon bond is much stronger than the hydrogen carbon bond, and that should slow down the oxidation. And since we can put many of these in the membrane, not just 1 per 1,000 in principle, it might help, okay? And so I'm going to talk today mostly about deuterated linoleic acid, a molecule called 1111 dideuterolinoleic acid. On some slides, it may be called by its drug name, RT001. Just in passing, I want to point out that we have this stuff, which is 1,000 times more potent than deuterated linoleic acid, but we don't yet have permission to give it to people. So I can't give you any clinical results, but it should be very, very promising, okay? Now, right away, if you think about this for a second, you're going to realize that there are issues here. You're not going to stop eating linoleic acid. We've actually tried to put patients on low linoleic acid diets, and they're very unhappy, okay? So we have to give you enough of this stuff in your diet every day as pills to compensate for the stuff you're eating, okay? So we are giving this at non-drug doses, typically 5 grams a day. Okay, so it's a lot of pills, okay? Or for infants, as you'll see in cocktails, in milkshakes, okay? The moment I heard this idea from Misha, the reason why I knew it had to work, and the why I started a company around that one idea and invested, et cetera, is because why do most drugs fail in clinical trials? They either fail because of toxicity, or they fail because of what's called bioavailability. They don't get to the target. Okay? This can't be toxic, okay? There's no way, there's almost nothing in the body that can tell the difference between whether there's deuterium there or hydrogen there. These are not even exchangeable deuteriums. They're not going to move around, okay? And your body has an elaborate system of transporters and receptors to take these very precious fats that you eat and make sure the eye gets the ones that it wants, and the brain gets the ones that it wants, and every tissue wants different combinations, and all of that is set up. So we knew at the onset that if we could simply make these compounds, that the body would use them efficiently, okay? Now, to make a long story short, the effect of deuterium on chemical reactions is hard to predict. It can be a small effect, it can be a big effect, and we got fantastically lucky because in this case, it's a gigantic effect. So deuterium slows down these reactions by a factor of 10 to 30-fold, which means for all practical purposes, it stops them. Second, and this we have hand-waving explanations, but no proof. We don't have to substitute every fat in your body. We have to substitute roughly 20%. And that sounds absolutely scary, except we're making a trivial substitution. I mean, stuff you eat every day. We've just put 2 extra neutrons in it, okay? And in roughly a month to 2 of dosing, you reach these levels in animals and, as far as we can tell, in people, okay? So the very first experiments that were tried were stellar, as I'm going to show you, and they were actually done by Kathy Clark at UCLA. So this is yeast. Talk about model organisms. We started at the very beginning, okay? This is yeast. This is called dilution plating. You're adding less and less yeast cells growing on a surface. Yeast has no linoleic acid. Doesn't make it, doesn't know it, doesn't need it. And normal yeast doesn't care about it. But if you make a mutant yeast that's sensitized to oxidative damage, what you can see in the second panel from the left, called linoleic acid, is that linoleic acid is absolutely fatal to oxidatively compromised yeast. What you had for lunch kills this better than a doornail, okay? If we put the deuterium in the right place at the carbon that gets oxidized, you can see we restore the wild type behavior. And if we put the deuterium in the wrong place, it has no effect whatsoever, okay? So I think you can begin to see why we have 80 academic collaborators all around the world, and all we do is send them these molecules, because we have perfect controls, okay? If you get an effect on an animal or a cell or a human by moving the deuteriums from there to there, you know what the mechanism is. Okay, so we worked on all kinds of disease models. These happen to be cell models. I don't want to spend much time on them, but this is a model for Parkinson's. It's Parkinson's cells, and they get killed by oxidative damage. They're actually being painted here with alpha-synuclein, but linoleic acid protects them. This is an Alzheimer model, one of quite a few we've looked at. Again, if you poison them with iron or something called HNE, which is a fat oxidation product, you kill most of the cells, but if they have deuterium in black bars instead of hydrogen in gray bars, they are fine, okay? This is a disease we're going to talk about a little bit in a few minutes, Friedreich's ataxia. It's a rare disease. These patients, if they eat what you ate for lunch, linoleic acid in blue, it's toxic, okay? You see, this is why this is a paradox. They have to eat it, okay? But it's toxic. And on the other hand, with deuterium, at least the cells, it helps them. Okay, so let me just say two more things. These deuterated fatty acids can cross-protect. We don't have to deuterate every one of them. Just one type of fatty acid will do it. And we have to get to somewhere between 20% to slow the reactions completely. But even at 5% substitution, we see effects. All right. So what you do at this point is animal tox, okay? So you take some poor rats or mice, and you make them live on this as their sole source of fat for several months. And you ask two things. Does it hurt them? The answer is absolutely not whatsoever. No harm seen at any level of cellular or anatomic pathology. And then, since it's an animal, you can sacrifice them and ask, where does it go? Okay? And so this is a brain of mice. We've reached about 30% deuteration, so we're above that 20% level. And they, this is the linoleic acid that they were fed. These mice were also fed at omega-3. And you can see in the brain, there isn't any linoleic acid. It's all been elongated to arachidonic acid. And once again, in the brain, there isn't any linolenic acid, which is a small chain omega-3. It's all been processed to DHA. The blue is the deuterium. It's very easy to do this by mass spectrometry. So these are really trivial experiments. And you can see basically that the adjacent colored bars are mice that got just hydrogen or just deuterium. And you can see by the end of 3 months, where not only are we getting good substitution of all of these products, but we're not changing in any way the downstream metabolic profile, okay? So it's like the body doesn't know we're doing this, except that the fats aren't burning, okay? Now, we've done much more elaborate studies, and I wouldn't dare to show them to you. But the bottom line is, if there is any effect at all on normal metabolism of having these deuterated hydrogens present, it's anti-inflammatory. If there's any side effect at all, and we've not seen it in animals or patients yet, it's going to be anti-inflammatory. So that's a good position to be in. All right. So we then went to animal models of disease. And I asked Misha to prepare this slide, and he got carried away. And I don't like busy slides, so I don't want to say anything about this slide, except that we've looked at probably several dozen animal models at this point, and either two things happen. Nothing has ever been in between. Either we have no effect whatsoever, and from that we conclude that oxidative damage is not involved in that particular animal model, or we have dramatically large effects in Alzheimer's, Parkinson's, diabetic retinopathy, you name it, all kinds of models, okay? But what I want to do in this talk is concentrate on human data, just to show you how this is really playing out. Okay, Friedreich's ataxia is an orphan disease. I think there's about 12 to 15,000 patients in the US. It's only in Caucasians and in people from India. No other population has this disease. It's a loss of protein function. The protein that's lost is in the mitochondrion, and it's an iron chaperone. And these patients don't have it, okay? So because they don't have this iron chaperone, they have free iron in their mitochondria. Free iron oxidizes fats. I won't, again, bore you with the details, but we don't replace the missing protein. This is not gene therapy, okay? We're not going to cure this disease because these patients are missing an essential protein. But the major effect of missing that protein is fat oxidation, and that we can stop, okay? And does it help the patients? And it seems to. So this is the results of a phase 1 clinical trial, 18 patients, 12 cases, 6 controls. When you ask these patients, and I've met many of them, what's bothering you? I mean, they know they're going to die in their 30s of cardiovascular disease, but what's bothering them, even though it's an ataxia and they have bad balance because they don't know where their limbs are, they're exhausted. If they just go to the store and buy something, they have to go to sleep for a while. That's how they have no energy whatsoever. So Peter Milner, our chief scientific officer, realized that the easiest way to detect this disease would actually be to use a cardiovascular endpoint, and this is the peak workload that these patients can generate on an exercise bike. 2 of our patients couldn't find the pedals, so that's why the number is not 12 but 10. And anyway, after 28 days of treatment, you can see that we're showing improvement in the peak workload compared with placebo. Okay, a year of fighting with the FDA, we won. Let us convince them that we could use a cardiovascular endpoint for a neurological disease. Obviously, it's a neurological disease. Our application went into the neurology section, and they don't know from cardiovascular disease. But that's the approved endpoint. We're about to enroll about a 70-patient pivotal trial. So what that means is if the 70 patients do what these 18 did, we'll get approval. Okay. So that looks good, but this one looks better. Now, this is a disease. I would be astounded if any one of you has ever heard of this disease before, even if you're a neurologist, okay? This is called infantile neuroaxonal dystrophy. We had never heard of the disease. And how we got into this disease is a simple and true story about how science really works these days. We had sent the compound to a Parkinson's group at Imperial College London. Somebody down the hall, looking for something to do, borrowed some of the compound. We didn't know about this. They didn't have permission to do that. And they were looking, they had made a fruit fly model of this disease. So this disease is complete loss of function of an enzyme that repairs oxidized fats. Okay? The Friedreich's patients had too much fat oxidation. These patients lacked the ability to repair oxidized fats. And they treated the fruit flies, and the fruit flies got better. And they tried to publish in that, well, I don't know what journal it was, the journal editor said, you know, we're not going to take a fruit fly model for a human neurodegenerative disease, at least get some patient cells. So they got some patient cells and treated them with the drug, and the cells had much better viability. So they published. And then the parents of one of the children who had this disease tracked us down. And we're unbelievably persistent. And we didn't want to go near what's called expanded access. You're allowed, with doctor's permission and FDA permission, to give a drug that's not been FDA approved, even to a kid, if everybody will sign off. Okay? So this is look, this is really a devastating disease. I'm going to show you one patient. They present between 6 months and 3 years, and they die. They progressively lose developmental milestones, and depending on, usually they die from feeding tube complications. And a lot of the problems with this and other diseases are bulbar. They can't swallow, they can't talk, they salivate, and so on. Okay, so we have been, this is our first patient, the only one I'm actually going to show you. Rather than read all this stuff, I'm going to show you some movies, okay? This little girl was predicted to be dead in 6 months when we got her, and she's very much alive. Let's see if I can do this. So when we got her, yeah.
All right, let's check your muscle.
She's a vegetable. her eyes don't focus. If you try to lift her up, she can't support her neck. She's completely uncommunicative. It's really sad. And you can see why the parents were extremely aggressive at trying to get us to give this little girl a drug. Oops, let's see. Oh, maybe it's not working. No. Oh, yeah. So now this is 6 months on drug. You see she's holding her head up. Okay, so this is really dramatically improved. And let me stop that. Oops, I'm sorry.
Where's my eyes, Aria?
So now this is a year of 10 months actually on drug.
Higher.
She's communicating. She's a person.
Where's my eyes?
Keep
Keep going.
and focus.
Where are my eyes?
Okay.
Good girl.
Yeah, so I mean, now obviously she's also 10 months older. Okay, so this is a confounding factor. But
Who says that's
okay. So on the basis of this and one other patient, we have FDA approval for a pivotal trial in this disease, which is fully enrolled and ongoing with 20 patients. And we just keep our fingers crossed that if we see anything like this with a few more of those patients, then this is going to be great. Okay, but that's not even the best case. Okay, I'll show you the best case. Another disease I had never heard of before. I think it's slightly more common. It's a lysosomal storage disease. But many lysosomal storage diseases, the problem is that they're storing oxidized fats. And they have all these inclusions of oxidative fats which are leaking out very toxic products. And this little girl, after 1 month, had shown remarkable improvement. Okay, 1 month, okay? And let's go to the next slide. So here she is before treatment. And if you just look at what the leg is doing, you see that she doesn't have normal leg reflexes at all. It's going into tremors. And that's because her spinal cord neurons are not properly connected anymore to the leg because they're not functioning. And you can see after 1 month, she has now proper leg reflexes, okay? So let me stop that. This is all being done under what's called expanded access. The parents get their doctor to write, we send the drug, we're not allowed to charge for the drug. But we're not just doing this on small numbers of patients. We're doing this on large numbers of patients. The FDA is allowing us to experiment on humans because they are convinced that this drug is totally safe. There's no downside, okay? And our largest effort is now in ALS. So as you can see, we've got, 7 different centers, and at Mass General, there's just a huge enrollment of expanded access patients. Okay, so I'm going to show you results of the first of these patients, the only one that's been on the drug for a long time, or was on the drug for a long time. Okay, so prior to getting the drug, you can see on the left, this ALS patient is declining. Typically, ALS patients die 3 years after they're diagnosed, okay? So declining, typically close to death, but we kept him alive for almost a year before he eventually died of some kind of respiratory failure, okay? So on that basis, lots of patients are being tried. Okay, so I'm going to skip a few more diseases. I think you've probably seen enough. It looks good. This is a section on inflammation. So I felt I had to have an inflammation slide. Look, inflammation is another case where you have many possible biological insults which go through a common pathway, which you heard about in this morning's talks, lead to a bunch of different things we call diseases, okay? So basically, one class of drugs treats many different diseases. Our argument is that it's the same way. We have many different insults. That's the defect in the little girl that I showed you the first movie of. That's the defect in Friedreich's ataxia. That's the defect in Parkinson's, in Alzheimer's, and so on, producing various different disease outcomes. But they all have in common fat oxidation. And fat oxidation is something that we now know how to stop. Okay? Now, you might ask, is there any good about fat oxidation? Is there any reason why you'd want to oxidize your fats? And the answer is, as far as I know, the only thing it's used for is to induce enzymes to repair oxidized fats. Okay, so maybe not. All right, so this is very early stage. It's small numbers of patients. We have a lot more work to do, but I can only tell you everybody associated with this effort will take this prophylactically the day it's approved by the FDA. We're not allowed to take it now, but we're all lined up. We'll pay for it. We want it, and so stay tuned. Thank you.
That was tremendous. What a great talk. So questions? I'll start with you.
So another fatty acid induced disease is non-alcoholic steatohepatitis, which is super common, as you probably know. I mean, about a third of the population now has fatty liver, so is going down that road. Have you tested it in any of those?
So Chunming, who will talk tomorrow, has compound and is testing it on a NASH model. Yeah, but I don't know that there are any results yet. Yeah, it's a great suggestion, and yeah. I mean, oxidative damage just crosses so many different diseases. It's really a curious situation. Yeah.
So can this potentially be used as a nutrient supplement for normal people?
Yeah, exactly. So what we have, this is, you learn the hard way. You make mistakes. That's how things move forward. Okay. It turns out that what you're not allowed to do by the FDA is turn a drug into a nutrient. Once we filed our IND on that first molecule, it has to be a drug. It can never be a nutritional supplement, okay? But you can go the other way. So with the second molecule and other molecules I haven't shown you, we're going to submit them to the FDA first as a nutritional supplement, get approval that way, which is a piece of cake. All we have to do is show it doesn't kill you. And seriously, and then we'll turn it into a drug. But we're never, unfortunately, the first one is ruined. And I'll tell you, ironically, the first one, which is the one in people and is the least effective, is the most expensive to make. So it's too expensive to be a nutritional supplement. All the others are cheap to make, and because we can make them catalytically, but we can't make the first one catalytically. So they're going to be more suitable to the price range of a nutritional supplement. We definitely will go that way. And then, of course, we don't need a large clinical trial to justify selling it.
I've been on fish oil for 15 years, and I've tried to go off of it, and I end up in terrible pain. So is there something I can do to make it less damaging in the future?
I recommend, I don't take fish oil, but I eat a lot of fish, right? I recommend that you keep it frozen and out of the light. That's the best you can do. I'm sure that most commercial fish oil products are heavily damaged. Obviously, you do need it. Again, fish oil, DHA is an essential nutrient, or some omega-3 is an essential nutrient. You must eat it, so you have no choice, but try not to eat the damaged stuff.
Hi, so thank you so much for this talk. I'm interested, since we're in the state of Colorado, and since this state is the poster child for what's happening kind of nationwide with marijuana and cannabis, and the interest in the non-psychoactive CBD, cannabidiol, which supposedly has powerful anti-inflammatory effects. And I'm just wondering, is there any research to show anything linked to what you're talking about here?
So I don't actually know the chemical structure of cannabidiol, but just from the name, I would guess it's easily oxidized and therefore potentially subject to the same sort of problems. But the difference, look, many things oxidize, but as long as they don't oxidize in a chain reaction, if you eat some antioxidants, blueberries are probably the best. Any dark food, by definition, the colors are all antioxidants, okay? So any dark-colored food you eat is going to be rich in antioxidants and is going to help against these non-chain reaction things. The hideous thing here is that in these membranes, where these oxidizable fats are packed close together, that's a really no-win situation.
So I think in your list, there was nothing about longevity and aging, or at least I didn't see it. So would you say something about that?
Yeah, actually, okay, thanks, Larry. So Misha Shepanov, the guy who thought this up, his original thought was, we're going to be an anti-aging company, okay? Like many young Russians, they're very obsessed with longevity, okay? And a lot of our money comes from people who support longevity work, okay? And I don't like longevity as an endpoint, as a clinical endpoint. It's simply a horrible clinical endpoint for all sorts of reasons. But the diseases I'm talking about are all age-related diseases, except for the rare genetic ones. They're all age-related diseases. So I'm very much aligned with Larry that I want to focus on health span rather than lifespan. And if we can make people, especially with these neurodegenerative diseases, which are so costly to manage, if we can relieve some of that, we'll be doing a great service to the world. However, it's been impossible to resist longevity studies in model organisms where they're feasible. And we actually have some gorgeous data on nematode, which is about to be published. And if you want to believe worms are people, well, some people are worms for sure, but anyway, if you want to believe that, then this may promote longevity. We have some mouse data, which is also not as compelling and was much, much more expensive to generate. But it's statistically significant. It suggests that we do increase mouse health span and lifespan. The trouble with that data right now is that it was done on one particular inbred strain of mice. And one of the reasons why you can almost never generalize from mice to human is because they're inbred and we're not, okay? So this has got to be tried on a whole bunch of different inbred strains of mice before there's any reason to believe the results on one of them. And we haven't done that yet, and it's a very expensive experiment, and it's not high on our priority list, but it'll happen.
I want to tell you, I'm in favor of longevity.
Has the FDA asked you to look at mitochondrial functions as a test to make sure that when you have heavily deuterated linoleic acid in the membrane, that all the mitochondrial functions are normal?
Right, okay. So they actually have not asked us to do that per se. The reason probably that they haven't asked us is long ago in model systems, we did look at mitochondrial function. And just the opposite of hurting mitochondrial function, this stuff helps mitochondrial function, okay? So, because even in a normal mitochondrial assay, there's oxidative damage, and we're suppressing that, okay? So something called the seahorse assay, anyway, we passed that with flying colors, so it's not been an issue. So I'm willing, I have to tell you this, and you'll understand how complicated the politics of this gets. The FDA was willing to grant us an exclusion from tox studies, because there's a rule that a deuterated compound, if the compound is safe, automatically the deuterated compound is considered to be safe. And the reason why this rule came about is not just serendipitous. It's because deuterated compounds are used as metabolic tracers all the time, okay? And so thousands of deuterated compounds have been in man, and much of what we know about metabolism, it comes from deuterated compounds. So,
What about the membranes, things flow back and forth between the mitochondrial and the cytoplasm.
right.
And what about all the succinate, it goes back and forth, and when it goes out, it's toxic?
Well,
In the water, so they didn't ask you any of that?
no, they didn't, right. Again, no, they didn't. What can I say, right? Maybe they should have, and yeah.
I'm going to have to stop, but I must tell you that was a phenomenal talk, and I really appreciate it.
Thank you, right.